Alright, hi everyone, welcome to my YouTube channel CCF Electrons, and in this video we'll talk about Newton's interpolating polynomial. Okay, so for Newton's interpolating polynomial is among the most popular and useful forms of expressing an interpolating polynomial. Note that the simplest form of interpolation is to connect two data points with a straight line. Very simple. This technique is called linear interpolation and is shown below. That is, if we have this point, we have this point, we have this point, just use a straight line. That's the simplest form of interpolation. Connects two data points with a straight line. Okay, here we have this. This is f of x and this is x. Okay, you see as they correspond, x corresponds with f of x, x1 corresponds with f of x1, xn corresponds with f of xn. And looking at this we can see a triangle from this. Okay, you can see a triangle. I think I should have added a 1 here. I should added a 1 there. Nope. Oh boy. So okay, I hope we are following. Yeah, I should add a 1 here, and this one means it's first order. Okay, order 1. So the above diagram is a graphical depiction of linear interpolation. The shaded area indicates the similar triangles used to derive the Newton's linear interpolating formula, using similar triangles from the figure. So let's quickly do that. Similar triangle. Let's quickly do that. Now, this is just like saying that x minus x1, which is this, x minus x1. Okay, so we are dealing with this small triangle first, this small part, before we deal with the complete triangle. So for this small part, x minus x1, that's what we have under. So we say, just like saying change in y over change in x. So f of x, or f1 of x minus f of x1, which is this top, and then the bottom, x minus x1, they're equal to the bigger triangle, f of x2 minus f of x1, which is this, divided by x2 minus x1, x2 minus x1. This is not xn, this is x2. Okay, that's x2. Okay, so this is equation 2. Our equation 1 is in the previous video. So equation 2 can be rearranged to yield this, just by making f of x1 subject formula. This one crosses this to become plus. Okay, and that cancels out this guy, and this this crosses this to become positive. This guy multiply both sides. Okay, so we rearrange to get this. So this Newton's equation, this equation 3 is in Newton's linear interpolating formula, and the notation f of x1 means that it's the first order interpolating polynomial. Okay, all right. So yeah, beside representing the slope of the line connecting the points, the term is a finite difference approximation. Okay, so we have definite points, like from this point to this point, this point to this point, definite points. Okay, now in general, the smaller the interval between the data points, the better the approximation. That is due to the fact that as the interval decreases, a continuous function will be better approximated by a straight line. This demonstrated by the following example. Okay, this is demonstrated by the following example. So what this paragraph means is that if the distance between one data point to another data point is very small, the approximation will be better. Okay, if the distance between the two data points is large, the approximation will be less accurate. Okay, so now let's try that and see. So estimate the natural logarithm of 2 using linear interpolation. Note that the true value of ln 2 equals this, of ln 2 equals this. Okay, so let's do that. So ln 1 is 0, ln 4 is this, ln 6 is this. So look at it. Since we are looking for ln 2, right? Since we are looking for ln 2, the closest place here is from where? Ln 1 to ln 4. This is closer now. Because ln 2 is between ln 1 and ln 4, is closer. Ln 2 is also between ln 1 and ln 6. But the gap from ln 1 to ln 6 is more than the gap from ln 1 to ln 4. Okay, however, let's just take the approximation from ln 1 to ln 6, see our answer. Take the approximation from ln 1 to ln 4 and see our answer. Let's see which one is closer to the true value. So for ln 1 and ln 6, we apply the formula. Okay, f of x1 yada yada, this and that and that. So so this is the lower limit, that's the lower value, this is the upper value. So f of x1 will be what? Lower value is what? 0. Okay, higher value is ln 6, so we'll put that value here, ln 6, we'll put it here, minus lower value, which is 0, multiplied by x. X is what? We are looking for ln 2, right? We are looking for ln 2, so x is what? 2 minus x1. What is x1? Which is this value, ln what? 1, so 1 will be there. Okay, so when you simplify, divided by x2 is what? 6, x1 is what? 1. Note that the x's, they are this value, the f of x's, they are this value. Okay, the x are this value, f of x are this value, x is this value, f of x is this value. Okay, so when we do that, this is the higher limit is what? 6, the lower limit is what? 1, x. So that will give us this. Are you seeing the value? Okay, so this value we got. Okay, now let's use using a smaller interval from ln 1 to ln 4. We've tried ln 1 to ln 6. Look at our answer. Let's try from ln 1 to ln 4. Okay, so let's go. So when x is 2, of course the lower limit is 0. Okay, lower limit is what? Ln 1, and ln 1 is what? F of ln 1 is what? 0. F of ln 4 is what? This. Did I say f of ln 4? F of x, which is ln 4, gives us this. Okay, minus 0. Why? Because that's a lower limit using this formula. Okay, x minus 2. X is what? 2. We are looking for ln 2. But s1 is what? The lower limit, which is this. Then we get this. Then for this one's under is what? x2 minus x1. Upper limit 4, lower limit 1. So we get that. Let's see our answer. 0.46. Okay, so for this one, look at our value, 0.3 something, here 0.4 something. So let's look at the true value. The true value is 0.6. And can we see that when our interval was smaller, the answer is closer to 0.6 compared to this one? Okay, so that's just the idea of the difference in interval. Okay, now for quadratic interpolation, that's the second order, f2 of x, we have b1 plus b2. Now for the first, it's almost like this. Just bear this in mind. N and then x minus x 1. Okay, and then you have n on n minus 1 on top. So of course this is the first place, so here is 1. Okay, and then what you have next is what? 1 minus 1, that's 0, so everything here will just be 1. So you have b1 in the first case. So the next case here will be 2, so you have b2. 2 minus 1, here will be 1, so you have this term present here, and so on. But this guy doesn't turn to 2, please. It doesn't turn to 2, but it gives you x minus x1, x2, sorry, x minus x1. Then the next thing you now have x minus x2. Then okay, so this is it. So I think, well, I shouldn't put this minus x1 on top. That thing I shouldn't place that. Okay, but I hope we get the gist. Okay, so just bear this formula in mind. And for that b1, it means what? F of x1. That's mean of b1. Okay, so if you substitute this b1 into this equation, okay, you arrive at b2 being this. Similarly, b3 being this. Okay, now a way to think of it is that we are seeing it as we are seeing it as b1 equals f of x1, b2 as what? F of x2 comma x1, b3, this is a short way to look at it, x3 comma x2 comma x1. This is a short way to look at it. Okay, so what this means is just f of x1, but this guy f of x2 comma x1, it means we are going from x2 to x1. Are you seeing it? Going from x2 to what? We subtract x2 from x1, so f of x2 minus f of x1. But for the third one now, we are going from x3 to x1, so we have it here, x3 minus x1. Whereas meanwhile, on top of it you have what? x3 to 2, x2 to 1, and of course once you have x3 to 2, this will be f of x3 minus f of x2. Similarly, I have it this way. Okay, that's clear. So the example here just says employ a second order Newton polynomial to estimate length 2 with 3 points. So they have given us x1, x2, x3, f of x1, f of x2, f of x3. So all we have to do is just to put in the values. So find b1, b2, b3, and then substitute into the equation. That's all. So b1 of course is this 0, b2 is this, so you just plug in the value. What is f of x2? Look at it, place it there. What is f of x3? Okay, what is f of x1? 0, you place it there. Okay, x2 is what? 4, x1 is what? 1, just like that. So that's how you get your b2. b3, just like I said, just like the way I explained, x3 is what? 6, you place it there. Okay, x1 value, you place it there, x2, just substituting the values like that, and then we got b3 as this. Then we'll come to our formula and substitute in all the values. Which formula? This formula here. This formula here. b3 we have solved for it, you put it there. b2 we have solved for it, you put it there. b3 we have solved for it, you put it there. x2, x is what? We are looking for length 2, so x should be what? 2. X should be what? 2. x1 we have it, x1 we have it, x2 we also have it. So you just substitute in the value and you get that. Okay, of course, please let me know in the comment section if you are following or not, or what's happening. Okay, like I said, this class recap, and we're actually making recap here. So for the general form of Newton's interpolating polynomial, the third order is what we refer to as the general form of Newton's interpolating polynomial. which is this. Okay, so b1, this is just like the equation we have above, it's just like it. Okay, and b1, like what I wrote up there, just like this expression. Okay, so it's just that it's expanded in this case. So when we make use of it, you will see what's up with it. So it's just expanded in this case. In the other case, we stopped at in this formula, we stopped at b3. Okay, but in this case, they continued like b2 to bn, like continuously. Okay, that's just the difference with that. And our b3, we stopped at f of x3, x2, this, but they continued down. Okay, so that's just the difference with that. Okay, so I hope this helps, and I'll see you in the next video. Thanks for watching.